Okay, great. So it's there's so many talks to attend here. And I'm glad we can just sit down and have a conversation. Yeah, once finally. Okay, great. So we're going to chat, I guess, about error correcting codes and other packing problems. So, great. Oh, right. Okay, so I'll quickly introduce sort of the space where we'll work. So we'll start with a finite set, and an important example, of course, will be 0, 1 here. And I'll look at the metric space sigma to the n, where I measure the distance between 2 points x and y as the number of coordinates where they differ. Okay, and so in this metric, I can look at the Hamming. So this is called the Hamming metric. Hamming was the name of a person. The Hamming ball is what you think it is. It's the set of all points y which are within distance r of a point x. Okay, and and in this metric, I want to study a packing question, which is the following. So I fix a radius r, and I want to pack as many balls of radius r inside sigma to the n. Okay, and by pack I mean they should be disjoint. Okay, and the question is, what fraction of the space can you cover? Okay, so that's exactly the same question as how many balls can you fit inside the space. Okay, and okay, so this is the kind of question I want to talk about. So I'll quickly good. So whenever you get a packing like this, then if you look at the centers of all the balls that you took in your packing, then that's what I'll call an error correcting code. Okay, so an error correcting code is the set of centers of balls in such a packing. So an equivalent definition is it's a set of points such that any two of them are of distance at least 2r apart, and because in this case distances were integers, at least 2r plus 1 apart. Okay, and so it's a set of points in your metric space that look far apart, that are all far apart from each other pairwise. Okay, and an important special case will be that of a linear code. So in the special case, when the finite set sigma you look at is a finite field fq, then if the code that you look at is a linear subspace, then I'll call it a linear code. Okay, so and so these are an interesting subfamily of the class of all error correcting codes, and often it's easier to think about questions like this. Okay, so let me quickly remind you about two continuous versions of these packing problems that might be more familiar. So the first one is packing balls in Rn. So you're in Rn, you have the L2 metric, you want to see how dense is the densest packing of unit balls in Rn. Okay, and so that's a picture from Wikipedia which says that sphere packing finds practical applications in the stacking of oranges. Right. Good. And a special case of this is a lattice packing, where the packing that you come up with, the centers of all the balls that you come up with in your packing form a lattice in Rn. Okay, and so apparently, so that's an example of lattice packing. Okay, great. So another question which looks very similar. So both these continuous questions will look a lot like the question about packing in Hamming space. And so there are similarities and there are differences, but okay, so here is another question that looks very similar. So now the question is on the unit sphere. Again, I look at L2 distance, and I fix a radius r, and I ask what is the densest packing of caps of radius r on the unit sphere, and this is in Rn again. Okay, so all these three are very, very well studied questions. So the second, so these two questions, the latest two questions have been studied for centuries, and the first question about packing in Hamming space is sort of a more recent question because of its applications to because of its applications. Right, n should be large. We're always going to be interested in n being large and sigma being a small fixed thing. Okay, and even in these two questions, I will not be concentrating on n equal to 3 or 24. It will always be n also going very large.
So if I look at this thing on it, so this is an n sphere, right?
This is an n sphere, and those are n minus 1 caps.
Those are n minus 1?
N minus, right. So these are
caps. Yeah.
These are caps, right.
So then do you know, you don't know what the optimal packing is in this case, or do you?
No, we don't know at all. And so I'm only going to hope to find, okay, so what is the densest was not the question. The question is, what is the density, or estimate the density of the densest packing, if you can. Right. Oh, I guess all questions have if you can anyway. So good. Okay, so why do people think about such questions? Well, first of all, these are very, very basic questions, so you should agree. I mean, it reveals to you very basic things. Yeah. Good. And so while thinking about it, use the questions that it makes you think about are even more basic. So this is another good reason. And there are other and there are many, many applications. Okay, but by far the most important, or not the most, oh sorry, I take that right. Another very important reason for studying such questions is for the problem of error correction. That's what gives these things their name. Okay, so, and this has applications in real life, in electronics, and various things. And so the application comes from the following observation. So whenever you have a set of points which are well spaced apart inside a metric space like a code or a lattice, then okay, so suppose I want to tell you about a certain point, or I want to tell you something, then I'll tell you one of these points, and in the process of telling you these points, even if a few mistakes occur, you will know what I'm talking about, because you will certainly never confuse this point to this point, because they're far away. Okay, so very roughly, if I take this point and I say transmit it by a signal, and then you receive something which is that point, then you'll never confuse. Then you will know which point I was talking about. Okay, so it helps you do a distinguishing problem. Okay. Great, and so this also has applications in many aspects of communication and computation, and another very important place where it shows up is in complexity theory. So it's not at all clear why it has any connection, but it helps us say something like, it helps us understand why questions like the P versus NP question have anything to do with randomness in computation. So this is the question of what can computers solve efficiently. This is the question of what can computers solve with the aid of randomness. And so we don't know how to answer either of these questions, but somewhere in error correcting codes we know the answer. We know that these two problems are very closely related. Okay, good. So the plan for the rest of this talk is, so I'll give you two very simple observations about how to construct such error correcting codes, and then I'll tell you three of the neat things that happened in error correcting codes, or three sort of surprising facts about them, and then I'll finally give you, I'll highlight one of the special constructions of error correcting codes based on algebraic curves. Okay, good. Okay, so the first thing is a strategy for constructing such error correcting codes based on greed. Okay, so I want to pack balls of radius r inside my space. So this is a general formula that works in all the three problems that I talked about. So, and the strategy is, as long as you can include another ball in your packing, do it. Okay, so keep including balls into your packing, and as long as you can keep doing this, do it.
Are you putting them in? You put them in randomly, or how?
So I don't specify. So just take any one, and so randomly is also a good strategy, but any one.
And you try to keep on putting it in.
And as long as there is a ball that I can add in without ruining the.
When you put one in, you can say, now my next one has to be very close to that one, or something like that. You don't do that.
No, I don't say that. For now, I don't say that. Yeah, one could try variations on that, but okay. But I'm only going to just take it arbitrarily. Okay, so the observation is that every new ball that you add in rules out a volume of 2r from the space of points where you can place a new ball. Okay, so so if I place this ball inside my packing, and this is a radius r, then I cannot ever choose a ball centered at any point at distance 2r, because if I place such a ball, then it will intersect with the ball that I started with. Okay, so each new ball rules out a volume of the volume of a ball of radius 2r from the space of possible things I could add in. And so this tells you the basic bound that the density of any such packing, or it is so this procedure can produce a packing of density at least the volume of the ball of radius r over the volume of the ball of radius 2r. Okay, so
But some of that volume you rule out may already be occupied by previous balls.
oh, that's correct. So if that is true, then you will get a packing with higher density, which is better. But this is giving you a packing of density at least this much. Okay, so this is a simple naive argument that gets you started on this problem. Okay, so I can take this and look at it in the problems that I'm interested in. So inside the space 0 1 to the n, the volume of the ball of radius r is about n choose r. So believe me. So when r is a constant, this gives you packings of density n to the minus r, and when r is of the form when r is proportional to n, then it gives you 2 to the minus constant times n packings of that density. In Rn, this gives you packings of density 2 to the minus n, and that you can see immediately. So I'm just to contrast, I mean, if you just started with the Zn lattice and use that to give you or a scaled version of the Zn lattice, and then try to do a packing, then this would give you a packing of density n to the minus Cn, which is much smaller. Okay, so this greedy kind of packing is doing something odd at least. Okay, and for spherical codes, something very similar happens. With very small radiuses r, the density is about 2 to the minus n. Okay, great.
Spherical code means that's the caps?
That was the caps problem. Yeah.
Why would Zn be so much worse than Rn?
Oh, sorry. No. This is sorry. I'm comparing what the density of the greedy packing gave you with just doing something like taking Zn. So Zn seems like a pretty neat and regular lattice, but it's a terrible packer.
Oh, okay.
You're right. You can take better lattice. Great. So another very general strategy for packing in metric spaces is by just doing it at random. So one strategy is pick some balls at random and kick out all the overlapping pairs. And this will do something like what you suggested. Another way of doing it is is when you have some kind of structure, then pick a random linear. So if you're working sigma to the n and sigma is a finite field, then you can pick a random linear space of the correct dimension uniformly at random, or you can pick a random lattice in Rn uniformly from the space of all lattices. That makes sense. Okay, and again, this gives you density at least exactly the same formula. Okay, so this gives you a packing of exact. Right. So, and in both these cases, it's known that this is with high probability too. So, a random lattice or a random linear space does give a packing of density this and no better. I mean, it gives no worse and no better. Okay. Okay. So, again, so it gives you exactly the same behavior. So if you're slightly careful while doing it with lattices, it will give you a packing of density 1.6 times 2 to the minus n. That's actually pi square over 6, I think. And for spherical codes, again, it will do something very similar. Okay, so these are two very generic strategies that seem to do something. I mean, that gives you a grasp on this packing problem. Okay, and so now we'll see some of the surprises of the thing. So the biggest surprise, one that really surprised me when I saw all this, is that this is the best we know. Okay, so so my packing strategies, both of them are very, very simple. I mean, of course, you feel like I mean, when you're picking.
That's the best we know for the Hamming situation.
And also for Rn, almost.
Because the way you get these dense packings is by choosing. You want some kind of random lattices, but they are random in a very restricted sense. You have constructions of lattices where there is some random element in it, but they are not really random lattices in your sense. So there are better packings. But the random lattice is in a more restricted sense than taking it in the space of all lattices.
Oh, I see. Right. So, but it is not much better. This is what the claim is. So I will come to that in a second. So, okay, good. So for the Hamming space, okay, the best node density something. So in Rn, the best node density for n large is that previous thing that I mentioned, the thing based on doubling times n. And if you remember, volume of Br over volume of B2R is 2 to the minus n, and this improves it by a factor n.
All I'm saying is that in Zn there is a packing of Euclidean balls,
Mm-hmm.
which has a density which is a constant minus n for an appropriate Swastik for an appropriate lattice.
In Zn there is a
Yeah, so you can find not Zn, but a lattice.
uh-huh. Oh, there is a lattice
A lattice packing of Euclidean balls with density constant minus n.
constant to the minus n.
Constant, not but because you're of n minus n. In
Oh.
Zn it's constant. It's n minus n, right?
Right.
You can find instead of Zn, you can find another lattice.
Oh, right. I agree. So that a random lattice serves that purpose. So I think yeah. So here, you can get 2 to the minus n times a constant by a random lattice.
This is a lattice packing?
This is a lattice also by picking a uniform lattice from the space of all lattices. Yes, yes.
But it's still 2 to the minus n, don't you?
But it's still 2 to the minus n.
No, because before, okay, yeah, okay, good.
Oh, okay. Okay. So after thinking a lot about it, maybe being clever about your random choices or being clever about your greedy choices. No, I mean, so here I really used absolutely nothing when I did something greedy. I said, I mean, just pick any point that is potentially valid. So after doing a lot of clever things, the best known densities are just by a factor n larger. So recall this is 2 to the minus theta n, this is 2 to the minus theta n, but we can only improve it by a factor of n. And it's not, and I should also point out that it is known that it should be as small as 2 to the minus some other constant times n, but the value of that constant is not, I mean, the values of the two constants don't match at all. Okay, good. So I consider this a surprise. The next two surprises are not such big. Oh, sorry. The second one is definitely a big surprise too. Okay, so that's surprise one. Yeah, surprise. Okay. Now, so the second one is that there are perfect and near perfect packings in Hamming space. Okay, so in sigma. So remember, we are packing balls. Balls are not cubes. So I wouldn't expect balls to be able to pack and nearly completely fill up all of space. So, but such configurations do exist. Okay, so the first one is somewhat simpler. It says that when you can pack balls of radius 1 in sigma to the n perfectly. Okay, so there is a configuration of right. So the density is 1. I mean, they're disjoint and they cover everything. That's pretty odd. Okay, and in 0 1 to the n, when r is a constant, so we're packing balls of a constant radius, there are packings with constant density. Okay, so earlier, I mean, this doubling argument or the greedy and random argument showed you that there were packings of density n to the minus r. Now there are packings of constant density. Almost all points are covered by these balls. Sorry, a constant fraction of all points are covered by these balls. Okay, and these are based on certain strange additive configurations. So I'll just state what the configuration is. So it's a subset S sitting inside f2 to the n, such that the size of S is 2 to the n over r. So it's the rth root of the size of the whole space. And if you look at S plus S plus S r times, so this is the sum set added to itself r times, then the size is precisely the cardinality of S, choose r. Every r tuple sums to a different element. Okay, there are sets of, I mean, for every r tuple to sum to a different element, the size of this set cannot be any larger than 2 to the n over r. but you can get sets of size exactly that such that every R tuple sums to a different element, and such things exist. So this is already a surprise, I mean, in this setting. So I mean, it translates into a good surprise there too.
So by the best we know in surprise one, that you can construct by some method, or?
Oh, right. So these are called Hamming codes. If you, right, and this, so I know exactly how these look, and I also know how these look.
This is not what you make with expander graphs.
No, this is not what you make with expander graphs. Expander graphs give you codes, yeah, which aren't even as good as this, but they do give you, I mean, some density 2 to the minus theta. Okay, so okay, right. So the third surprise, well, it isn't really a surprise, but earlier I used to call these nuggets, and well, it is certainly a nugget. So you should think this is nugget one. So there's a closely related problem, which is the covering problem, which is how many balls of radius r do you need to cover the whole space. Okay, and so the nugget is that this problem we understand very well. Okay, and so it looks very very closely related to the packing problem, but this we understand completely. So right, so and it says that the random covering is nearly optimal. Okay, so and the reason is well, coverings is okay for something to be a packing. All it takes is 1 point to be, or 2 points to be really close to each other, and it's no longer a packing. But for coverings, it's somewhat less delicate. If you throw in lots of spare points, everything is fine. Okay, so this is nugget number 3. Okay, so I'll wrap up with. I mean, how much time do you have for this conversation? Huh? Okay. Okay, great. So I'll give you 2 examples of very interesting codes. So the first one is a very basic one. It's just good to know, and it's based on nothing at all. Okay, so I'm working on the alphabet sigma, which is a finite field of q elements, and I take n points sitting inside fq, and I pick an integer d which is less than n. Okay, so based on this, I'll now produce a code. So this code is a subset of sigma to the n, and it's defined as follows. It's an n tuple, right? It's sitting in sigma to the n. Take a polynomial of degree at most d, and evaluate it at each of the xi's. Okay, then this gives you some set of points sitting inside sigma to the n. The number of points is q to the d, because I mean, there are that many polynomials like this, and right, and this is your code. Okay, and so I want to say that any 2 points in this code are somewhat far apart. So, and the reason is well, 2 polynomials of degree at most d can agree in at most d points, because the difference has at most d roots. Okay, good. So this is just a very simple idea which gives us some kind of codes. A very neat generalization of this is okay. So one thing to point out is, so this gives you a code over fq of size at most. Well, the length of the code is n, and n is better be at most q, because the number, because you want n points sitting inside fq. Okay, so so the question is, can I get a code which has q being fixed and n going to infinity? So there are no more than q points sitting inside fq. Okay, and so can I get codes with q being fixed and n going to infinity? And it turns out that some nice variations of this idea do work. Okay, so here is the idea. So one takes, and it's a generalization of what we just saw here. Here we evaluated polynomials on the line, univariate polynomials on the line. We just evaluated them. So now I'm going to take a curve in fq to the m. So it's actually f sub q whole to the m. Just okay. So and the claim is there exist curves with the following neat property. Whenever q is a perfect square, there exist curves with q to the m plus 1 over 2 points. So this is a little bit more than the square root of fq to the m, the square root of the size of the whole thing. There are curves with these many points, and their genus is q to the m over 2. So this is some kind of measure of the complexity of the curve. And the code is evaluate rational functions of bounded degree on x1 up to xn on all the fq points of this curve. Okay, and so it turns out you can do this. So you can fix q and pick a very large m, or let m go to infinity, and get curves in fq to the m with more and more points. I mean, even to come up with the defining equations of such a curve is not a joke.
So what you do then, you're looking at all, so x1, xn,
x1
points taken in x or what?
Yeah, right. So you pick a curve x over fq in fq to the m, and take all the fq rational points x1 up to xn. The point is there exist such curves with many rational points with genus not too large. Right. So that such curves exist is very magical. This exists. It's known to exist only for q being a perfect square. It's not known to exist, and probably not even conjectured not to exist when q is just a prime. Okay, and okay, so this gives us codes for with fixed q and n going to infinity, which are based on curves with more and more points sitting. So even with q equal to 4, I mean, you have a finite field of size 4, and you can get curves in f4 to the m with many points. And no, so this is a result of Ihara and Swasman Vladot Zink. Yeah, so right, so that such curves exist is a result of them.
No, I mean once you have to deal with intersection property.
Oh, right. Oh, I see. No, so it's just that
It's the same thing?
a rational function of degree at most d has at most d roots. This is the only factor. Okay, and so this gives you codes for every perfect square q with n going to infinity, and they're a very neat family of codes. And so one of the surprising things about this family is that once q is big enough, some large enough constant, then these codes are better than the random and greedy codes, and it's based on the answer to the question, what is the best ratio of the number of rational points to the genus of a curve over fq? And so the answer is known when q is a perfect square, and when q is prime, it's probably not right, and it's wide open. Great, and the reason why these things are codes that are better than random or greedy codes is completely mysterious. I mean, so I mean, why it is better than random greedy is okay, but the existence of, I mean, why should a specialized algebraic construction do something better than general principles? I mean, it's not clear why such things should exist, but they do. Right. So that was my last example. So I'm ready to chat. Yeah.
Yeah, in the case of the Hamming ball that you told us about, you had you get density which is of order constant, right? Which is independent of n.
Independent of n, but depended on that r, depended on the radius. Yeah.
Okay, but you don't know that those particular. So you have I guess with this construction you get them. But do you know that they're the best?
Yes.
You do.
So over 0. Wait. So are they the best? Oh, you mean the fraction of space?
Yes, exactly.
The fraction of space that they cover? No, we don't know that they're the best. Right.
There could be other.
There could be, right.
Which improve upon it in terms of.
Yeah, that's correct. Right.
Is it easy to describe where this is coming from?
Yes. So it is the follow. So let me do it for r equal to 2. Okay, that's already pretty neat. Okay, so I'll write f2 to the n as f2 to the n over 2 cross f2 to the n over 2. Okay, where so you know what I mean, right? I identify them by an f2 linear isomorphism. okay, then I look at the set of all points of the form alpha alpha cube sitting inside right where alpha is in f2 to the n over 2. Okay, and then the claim is that no 4 of these elements, no 4 distinct such elements can have a linear relation. Okay, so let's see why. So is the statement clear? I wanted to say that S plus S has size S choose 2. So that's equivalent to saying that well, okay, no 4 of them sum to 0. Okay, so or no 2, the sum of 2 of them does not equal the sum of any other 2, but we're in characteristic 2. So that's the same as the sum of no 4 is 0. Okay, so suppose alpha plus beta plus gamma plus delta was equal to 0, and alpha cube plus beta cube plus gamma cube plus delta cube was equal to 0. Okay, then well, I'm in characteristic 2. So if this happens, then I know that alpha square plus beta square plus gamma square plus delta square is also 0. And similarly, alpha to the 4 plus beta to the 4 plus gamma to the 4 plus delta to the 4 is also 0. So these four equations force that alpha, beta, gamma, delta cannot all be distinct, because the determinant of that matrix is van der Monde. Okay, so that's it. So because of the characteristic 2, something fun happened. Yeah.
Usually it's bad what happens, but there it's good.
Yeah.
So what about this polynomial? I didn't understand. So you didn't describe the polynomial, does it? Did you? Or
Those curves? No, I didn't describe them.
so, and where do they come from?
Where do they come from? So when they were first found, they are Drinfeld modular curves. So, but I don't know what those are. But later on, some people found explicit equations that cut out curves with similar properties. Right. So I mean, I can write the equations of those things. It's I don't know if it's illuminating or not, but so the equation. So it's in X.
This Drinfeld modular curve, is this from automorphic forms or what?
Yeah, I think so. Right. Okay. Yeah. So the equation is something like trace of xi plus 1 equals norm of xi plus 1, where q is so these are norms down to the square root of q. I mean, so q is a perfect square, and this is a norm from fq to f square root q, and similarly the trace is from fq to f square root q. I mean, the point is they're simple equations, right? And
So the x signs are in where?
they're in fq to the m, and the equations are
No, wait. The x signs are in fq.
each xi is in fq. Yeah.
And then you take the trace of fq over what field?
From fq down to the square root of q. So I needed q to be a perfect square.
And once you have that, from the definition, it's easy to deduce this property.
It's easy to deduce the number of rational points.